Okay, so we're going to do a little bit more factoring polynomials, and again, we're going to look at quadratic trinomials. I showed you last time that a quadratic trinomial is written in the form x squared plus bx plus c, and we used a method called pi and sigma, where pi is the Greek letter for P, capital P, meaning product. And so you're looking for two numbers that their product will give you C, whatever this value of C is, and their sum will give you B, whatever this value of B is. And we had a little method algorithm that we could fill in these blanks for the two numbers, two integers that multiply to give you C, but add the same two to give you B. Well, sometimes you get a number that's slightly different, and you may have asked yourself yesterday, why would she use B and C? Where's the A? Because in math, we always kind of start at the beginning. Well, sometimes you have a quadratic polynomial that has a leading coefficient, so that's the leading coefficient not equal to 1. So previously, the leading coefficient was 1 plus some number or some term with a numeral and a third term with a numeral. In that case, we would definitely use pi and sigma, and we'd use this algorithm of writing the two numbers that we come up with here. So say P and Q, then you can write P and Q, and you're finished because all you have to do is throw your x in here. X plus, and then x plus, and these are your factors. Okay, that was a quick review. But when you have a leading coefficient that is not 1, all of this falls apart. And so we need another method to adjust for when there is a leading coefficient. I call that magic numbers. Magic is spelled incorrectly because it looks like magic when we do it, but it's not actually magic, it's math. So we spell magic with a J to remind us that it's not actually magic, but good, solid mathematics. So I think before I do an example and throw some numbers in, I'm going to show you the method for the magic. Spelled with a J, of course. So what we're going to do, since having that leading coefficient changes all of this for us, we're going to make that leading coefficient disappear. And if you could see me, you would know that when I said disappear, I made air quotes with my fingers because it doesn't actually disappear. We're just going to manipulate it to look like it disappears. Magic. And then we're going to bring it back. Mathematics. So what we do to make it disappear is we're going to multiply A times C. So whatever A times C is, we'll make this A disappear. Then we'll do all of this exactly the same. Two numbers that multiply to give me A times C, but add to give me B. All of this is exactly the same, and when you get those, P and Q, then we have to undo the magic step. So remember, the magic step was to multiply A over to this side, and now we want to divide the A back out on this side to undo the magic process, because multiply and divide undo each other, right? So we're going to go ahead and divide this side by A. And then when we've done that, the magic is over. And so then I can just put in my x plus and my x plus, provided I left enough room. And now I fully factored that problem with the leading coefficient not 1. Something happened to my n. There it is. All right, so now let's do an example with some actual numbers to work with. So I have 2x squared minus 7x plus 3. Okay, so in this case I have a leading coefficient that's not 1, so I can't use straight pi and sigma method, but I can use magic numbers. And I'm going to multiply 2 times 3 to give me 6. 2 times 3 equals 6. Now, two numbers that multiply to give me 6, but add to give me negative 7. So remember, once we've disappeared the 2, I'm going to cross them out. Once we've disappeared the 2, then we're just looking at a problem, a pi and sigma problem, which we already know how to do it. So two numbers that multiply to give me 6, positive 6, but add to give me a negative 7. Well, that could only be negative 6 and a negative 1. Negative 1 times negative 6 is positive 6. Negative 6 plus negative 1 is a negative 7. Because I used magic numbers method, I created this magic number here, 6, by multiplying by 2. So now I have to divide by 2. Right, so that's finishing the process of undoing the magic. I don't know if I can make these lines disappear to make it. There we go. I undid the magic now, and so the leading coefficient is still there. Simplify these. Negative 3 and negative 1/2. Now I can bring in my x's. And then there's one last step that really does make the whole thing look like magic even more so, is I don't want an x minus 1/2. I want an integer here. I'm going to ask you just to trust me on this. When we get to solving equations, it'll make sense. I can rewrite this as x minus 3 times 2x minus 1/2. Excuse me, minus 1. All I did is move that 2 up in front of the x. So since I did so much hand-wavy stuff around here, I know you're expecting a rabbit to jump across the bottom of the screen at some stage, but I want to prove to you that I did indeed find the two factors that I would multiply to get this quadratic trinomial. So I'm going to write x minus 3 and 2x minus 1. Distribute 2x squared. Well, that's looking good, right? That's where I started. And then negative x minus 3 times 2 is negative 6x. And then negative 3 and a negative 1 is a positive 3. And if I combine like terms, I get 2x squared minus 7x plus 3. So this is the magic numbers method. Magic because it seems like a lot of magic, but the truth is method algorithms also often seem just like a whole bunch of magic is going on. It's kind of the nature. Completing the square is another one. The quadratic formula, when you're working with it, often these processes seem like a bunch of magic is going on. They're not. They're just algorithms to memorize, processes that you're going to duplicate every single time. Remember, the algebra is this step. Write the original problem and then write the factored form. So this whole middle part is a method for factoring quadratic trinomials. There are a bunch of methods that you'll use, and eventually you'll be able to factor problems like this without having to write it down at all. You'll be able, with practice, just to see the factors in your head. The same as, believe it or not, when you were learning to factor 6 into its prime factors of 2 times 3, believe it or not, that was really hard when you first learned it. And the trick that you had to use, which you never use anymore in this case, was the factor tree, right? 6 divides by 2, leaving 3. Or if you were factoring 18 into its prime factors, you used an algorithm. 18 divides by 2, leaving 9, and 9 divides by 3, leaving 3. And so that's 2 times 3 times 3. And believe it or not, this is no more magic seeming, or excuse me, is every bit as magic seeming in its day to you as this is today. So these method algorithms, you just have to go with the flow so that you become really good at factoring quadratics. So let's do some more examples just to practice. Negative 5x squared plus 7x minus 2. First thing we notice is there's a leading coefficient that is not 1, so we're going to use magic numbers. I'm going to multiply negative 5 times negative 2 to get a positive 10. I'm looking for two numbers that multiply to give me 10, but add to give me 7. 5 and a 2, and now I'm going to check the signs. They have to be positive to be a positive 10, either both positive or both negative. 7 is positive, so they're both positive. Undo the magic, divide by negative 5, and reduce. So I have negative 1 minus 2/5. Bring in my variable. And now I'm going to write the factored form. So I have x minus 1 times, I have to do that other little magic-y step, 5x minus 2. And now to show that indeed I have the factors, the two linear binomials that will give me a quadratic trinomial when I multiply them together, x minus 1 times 5x minus 2. 5x squared minus 2x minus 5x plus 2. 5x squared minus 7x plus 2. So you're probably saying, what the heck? That's not the same thing. But notice every term has an opposite value. This happens with factors, and I'm going to go back to integers in the number tree to show you that this has happened in your past as well. Suppose I'm looking to factor a negative integer, so negative 28. If I want to factor tree negative 28, the first thing I have to do is deal with the negative, right? So I have a negative 1 times 28, and then I can continue on and factor the 28. Let's see if I did it right, just because I was talking while I did it. And so negative 1 is a factor, and then positive 2, and positive 7. All the factors will be positive, except because the number is negative, I get a negative 1. The difference is with polynomials, just because there are minuses in the polynomial, notice this one had a minus in the polynomial, you don't really necessarily know, at least at this stage of the game, whether this is a negative polynomial or a positive polynomial. So when you get to the end and all of the signs are different, every single sign, so a negative is a positive is a negative, and a negative is a positive, what that tells you is that your polynomial is actually just a negative, right? So it's negative 1 is a factor of your polynomial. 5x squared minus 7x plus 2. If I distribute that negative 1, I get negative 5x squared plus 7x minus 2. And now it actually fits. And so all you have to do, and this is an important reason for checking your polynomials or checking your answers, is come down here and make it a negative 1. Throw in a negative 1, and this is, I could do it either way. I could write it as a negative 1 times the other factors, or I could just write negative like that. All right, so something that'll happen if you check your work and you get the exact same numbers but opposite signs, you just know that the original number was a negative. All right, so let's do one more example. I think the numbers are going to be pretty complicated, but there shouldn't be anything new to show you. We've covered pretty much everything there is to know in this at this stage of the game. So let's find the factors of 10x squared minus 3x minus 27. So these are all big numbers, and we also have a handler. I showed it to you last time, but we'll show you again how to deal with this. So first thing, I have a leading coefficient that's not 1. So I'm looking for minus 270. Two numbers that multiply to give me a negative 270, but add to give me a negative 3. So some of you guys are really good at seeing these kinds of numbers. Some of us aren't. I am not. And so the algorithm I use is I take 1 times, I just make a row of numbers. 1 times 270 is a factor pair of 270. We're not going to worry about the negative. That'll come out in the setting our numbers up here. 1 times 270 is a factor pair, the smallest factor on the left-hand side, and whatever the other member of the pair is. Can I divide 270 by 2? I can. 135. Can I divide 270 by 3? I think I can, because 7 plus 2 is 9, and we know that if you add the digits of the original number, if it divides by 9, it also divides by 3. So this is going to be 3 times 90. And now it gets a little bit easier, because in order for it to divide by 4, in order for 4 to be a part of a factor pair, 135 would have to divide by 4, right? So 2 times 2 gives you 4. So 135 divided by 2, that doesn't work. So that's not a factor pair. The next number is 5, and we know that it divides by 5 because 70 ends in a 0. So 5 goes into 27 5 times, leaving a remainder of 2. So 5 goes into 2, 0, 20, 4 times. 6, if I can multiply 3 by 2 to get 6, can I divide 9 by 2 to get a number? I can, 45. 7 is always the tricky one. Sometimes you just have to do long division on it. So 270 divided by 7. 7 goes into 27 3 times. And 7 doesn't go into 60 at all, so it doesn't divide by 7. 8, it doesn't divide by 8, because if it divided by, it would have to divide by 4 to divide by 8. 9, well, if 3 times 3 is 9, can you divide 90 by 3? 3 times 3 is 9, so 90 divided by 3 is 30. That works. Okay, let's check and see if I'm getting there. I have numbers like, I'm looking for a -3. So are any of these numbers different from each other by 3? They are not, but I seem to be getting closer, so let's keep going. 10 times 27, okay, that doesn't help us. 11, again, 11 just has to be, it doesn't divide by 11, but sometimes you just have to do long division. 11 goes into 27 twice, 22, 11 does not go into 50, so it's not 11. 12, well, 12 would be 6 times 2 would be 12. Does 45 divide by 2? It doesn't, so not 12. 13, another one of those divisor ones, or long division ones. 13 times 2 is 26. 13 does not, so that's not it. 14. 14 is a good number. Well, 14 can't be true because 6 doesn't divide, or because 7, if it doesn't divide by 7, then it can't divide by 14 because 7 is a factor of 14. 8, well, it can't be 8 because I don't have a 4. 9, oh wait, I went backwards. 11, 12, 13, 14, 15. 15 times 3, so 5 times 3 would give me 15. That means, can I divide 54 by 3? I sure can, and if I'm not sure, well, the way I know I can is 5 plus 4 is 9, and if I'm not sure what it is, right, I can do this. 3 goes into 5 one time, and then 24 and 3 goes into 24 18 times. 15 and 18 are separated by 3 integers. So this is a very methodical way, so that it took a little bit of time. It doesn't take as much time when you do it in the real world after you have practice, but it takes time when I'm talking you through it. But this will take you eventually to the very pair that you're looking for. Some of you are good at seeing these pairs, no matter how big this number gets. Feel free not to write this part out. But if you're not very good at seeing those pairs and you need a way to not just guess and check forever, this is an algorithm that'll help you out. Not required, just showing you how to do it when numbers are big. So I know it's 15 and 18 now. And all I have to do is decide which one is negative. If 127 is negative, one of these has to be positive and one has to be negative. In order for 3 to be negative, 18 would have to be the -1. Now, not forgetting that this is a magic numbers problem, I have to divide by 10 and then reduce. So I have 3 halves, positive 3 halves. So I can bring in my variable. And then minus 6, 18, let's see, 2, that's going to be 9 fifths. I knew I'd get there eventually. And so finally, all that work takes us to the second step of our problem. Remember, the algebra is step 1. Step 2, write the factoring. So this is going to be 2x, right? We're going to do that little trick. 2x plus 3 times 5x minus 9. And then, of course, you would want to check your results. I'm not going to because the video's gone into 20 minutes and I know this is the correct answer. I really wanted to show you that you have another baby step algorithm that you can use when the numbers are really big and they're hard to find. So there were a lot of little lessons in this video. Let's look. Well, one big lesson. When you have a leading coefficient, you can convert it and can't otherwise factor. You can convert this into a pi and sigma problem by using magic numbers, and then you just have to convert it back. 2 magical steps in the algorithm. Don't forget this one. We don't want to have fractions in our factors, so we want to just move that number up. Negative numbers can be a part of our factorization. It's obvious when we're dealing with integers, and so it never came up to have to ask ourselves about that, but it's not so necessarily obvious when we're dealing with polynomials. When you check your answer, if you find that your values are all opposite, then you just have to multiply the polynomial by a negative, which is what I did here. And then last but not least, not really part of the algorithm that we're learning, but certainly a baby step algorithm to use, finding factor pairs in a methodical way so you don't get lost in it whenever you're dealing with big numbers that you have to find factors for.